Hello, today we're going to do 8.1, which is testing the difference between means. What we're dealing with today is something called independent samples, and we're dealing with situations where we know our sigma and our sigma from another sample. So we're going to have two separate samples, and we're going to know our sigmas from both of our populations. What we're doing is we're learning how to tell the difference between what is independent and what is dependent. We're also learning what two sample hypothesis tests are, because so far all we've done is one sample hypothesis test, and then we're going to actually do a two sample z-test. Okay, so what is chapter 8? How does it differ from chapter 7? How does it differ from stuff that we've done before? In chapter 8, we're still going to be using hypothesis testing, so all that stuff about alpha and p-values and reject and fail to reject and all that stuff is still going to be involved in chapter 8. But instead of trying to figure out, is the mean 5 or something like we did in the last section, we're going to be figuring out if two populations are different from each other. So we don't really focus on what the value of the population is, like is the mean 5 or is it not. What we're focusing on here is this population different from this other population? So this way we can answer questions like, is the mean GPA of seniors significantly different than the mean GPA of freshmen? Because what we could do in a situation like this is maybe we have a sample of 100 seniors and then a sample of 100 freshmen. But and obviously if we find the mean GPA of those two groups of our samples, they're probably not going to have exactly the same GPA, because what are the chances? But we need to figure out if the differences between the samples are just because of the samples that we took, or do they represent a difference in the entire populations? Like maybe, freshmen haven't gotten used to high school yet and their GPAs are lower, and then maybe they improve and seniors are better, or maybe not. Maybe it's just everyone's, doesn't matter if you're a freshman or a senior. These are the kind of things we're going to try and figure out during chapter 8. Okay, so a two sample hypothesis test. It compares two parameters. Okay, remember that word parameters? That has come up all the way since chapter 1. Parameter means we're comparing values from populations. And again, if we had populations, we would just be like, oh, they're different, or oh, they're the same. But the problem is we don't have usually parameter values. We have sample values, and we use those samples to infer what's going on in our larger populations. Okay, so that's the same as it is from chapter 7. We have a sample, and we're using the sample data to figure out what's going on in larger populations. Now, when we're doing samples from two populations, these samples might be independent samples or they might be dependent samples. So when you have independent samples, it means you're dealing with two samples from two different populations, and those those samples are not related to each other. Now, that doesn't mean, they have nothing to do with each other. It's not like, oh, sample 1 is we're figuring out how much ice cream these people eat, and sample 2 is like we're figuring out how many trees are growing. It doesn't mean they're totally unrelated. It just means the individuals from the first sample have nothing to do with the individuals in the second sample. And I think the best way to really understand that is to look at what a dependent sample is. When we're dealing with dependent samples, sorry, I don't know if you can hear in this video, but there is a pretty large thunderstorm going on. So sorry if that is in the video, but it's weather, it happens. Maybe you'll find it soothing. Anyway, when we're talking about dependent samples, we have members in samples that correspond with each other. So a lot of the times dependent samples are going to be maybe a before and after test. So it could be the same exact people in sample 1 and sample 2. It's just a before they did something and after they did something. So it's the same people in each sample. Or a lot of times twins are used in dependent sample tests. They're called paired or matched. So maybe we would put one twin in, this experimental situation and one twin in like a placebo situation and see how they react to different things. But we're directly comparing that twin to that other twin, not everyone in the sample to everyone else in the sample. If you're a visual person, it looks maybe something like this. So independent samples, as you see here in this first picture, you just have two groups of people. A lot of times when you're dealing with independent samples, they don't even have the same number of people. So you just have one sample, you have another sample, and you just test them both and then you compare them. In dependent samples, you're looking at, you see like this person is directly compared to this person. This person is directly compared to this person, etc., etc. And those tests are done in a different way. So in this particular section, we're talking about independent samples when we're doing our tests. Dependent samples will come a little bit later, but it's still important now that we know what they are. So the first thing in this section is figuring out whether a sample is dependent or independent, because if you're, let's say, on a test, a chapter test, and the problem just says, hey, figure out if these two populations are different, you have to make the decision whether you're dealing with independent or dependent samples. Okay, so think about this. So in situation A, sample 1 is the weights of college students before their freshman year begins. We have 65 of them. And then sample 2 is the weights of those same 65 college students after their freshman year. Okay, so I want you to think about, obviously pause if you need to think about it or go back and read the definitions again. But I'm going to tell you, obviously, in a second. These are dependent samples, okay? Because we're dealing with the same people. We're going to take, let's say Sarah went to college and Sarah came back from college, and we're going to see what was her weight before, what was her weight after, or Bobby or whoever. But we're going to directly compare them to themselves. We're not going to say, oh, Bobby went to college at this weight and John went to college at this weight, and, compare Bobby to John. We're comparing Bobby to Bobby and then John to John. So these are dependent samples, okay? I don't know if you've heard of the freshman 15. It's like I don't know if it's a myth, but it's a thing everyone says they gain 15 pounds when they go to college. Maybe it's true, maybe it's not, but it's a thing that some people say. Okay, so our next one. So anyway, those are dependent because it's the same people where, this person before and this person after, we're doing a direct comparison. Okay, next one says we have the scores for 38 adult males on a psychological screening test for attention deficit hyperactivity disorder, or ADHD. And sample 2 is the scores for 50 adult females on a psychological screening test for attention deficit hyperactivity disorder. So if you think about that, it's not saying, oh, we took brothers and sisters, or, oh, we took these males before they took a drug and after. It's totally different people coming from totally different places. Maybe we don't know really much about them, but the big key here is that we have 38 in the first one and 50 in the second one, and there's no relationship between the people in the first sample and the second sample being discussed. So these are obviously not matched in any way or paired in any way. So these are independent. Okay? So you will have a few questions on a quiz or a test that just ask you to do this. Are they independent or are they dependent? So you'll have to make that distinction. Okay. So to read these two and do these real quick. Okay. So sample 1 says systolic blood pressures of 30 adult females, systolic blood pressure of 30 adult males. Now, these are the same amount of people, but these people have no relationship to each other that we can tell. We're just taking females' blood pressure, taking males' blood pressure. These seem totally independent of each other. So these are independent. Okay? Now, in part B, it says midterm exam scores of 14 chemistry students and final exam scores of the same 14 chemistry students. So basically, this teacher wanted to see, how did this student do on the midterm versus how did they do on the final? Obviously, they're going to compare that student to that same student on the midterm and the final. It makes no sense for me to, look at one of your grades on the midterm and then someone else's grade on the final and compare those, right? So we're looking at the same student paired with themselves on the midterm and the final. So those are dependent. Okay, so again, when you have a bunch of different types of problems, you're going to have to make that distinction. But in our case today, we're only dealing with independent samples when we're doing our math. So before we get to our specific types of cases today, we're going to talk about an overview of two-sample hypothesis testing. So in Chapter 7, we did one sample hypothesis test, or one proportion z-test. We did z-test and t-test. Now we're doing two sample z-tests and two sample z-tests. Two sample t-tests. So let's talk about here kind of what is going on. And like I said at the beginning, we're not testing values of parameters. So in Chapter 7, we might have seen something like, oh, I think the mean is 5 or whatever, or greater than or equal to 5 or whatever. We're not doing that in Chapter 8. So in Chapter 8, we're seeing, is there a difference between two populations? Okay, so in this one, your null hypothesis is going to state, again, some sort of equality, just like Chapter 7. It's always going to be less than or equal to, or greater than or equal to. But that null hypothesis, instead of being equal to a number, we're talking about equal to another population. So you might, and on the next slide it'll get more into detail, but you might have something like, I think mu1 is equal to mu2, okay? So your nulls and your alternates are not going to have actual numbers in them, except for these little subscript 1 and 2s, like mu1 and mu2. You can't just say mu equals mu. We have to, make it explicit that we're talking about two different populations here. So it's going to look something like that, where mu1 equals mu2. And then when we have our alternate, it's going to be the non-equality. So in this case, it would be like mu1 does not equal mu2. So our signs in the middle are less than or equal to, greater than or equal to, less than, not equal to, greater than. Those are the same as they were in Chapter 7, but we're now comparing a population to another population instead of a population to a value, okay? So these are what your nulls and alternates are going to look like, okay? So you have your straight up equality version, you have your less than or equal to and greater than version, you have your greater than greater than or equal to and less than. Now, regardless of which one of these three scenarios we're using, whenever we're actually running a mathematical test, we assume that our mean is 0, or that there's no difference between the two populations. So I'll show you what that looks like when we actually get to our formula. But we are going to assume there's no difference. Just like before in our Chapter 7, if we had, let's say, mu is less than or equal to 5, we would always assume, or put in as our understood mu, we'd put 5 in. Okay, so again, we're assuming there's no difference here when we're actually doing the math. Okay, and again, that'll make more sense when you see the formula. Okay, so now we're actually going to get more specific. So all that stuff that we just talked about was in general, kind of for Chapter 8, what your nulls and alternates are going to look like. Now we're going to focus on this section, which is about two sample z-tests. Okay, so just like in Chapter 6 and just like in Chapter 7, we can use z when we know sigma. Remember, if we have a sample standard deviation, that's when we use t. But if we have a population standard deviation, we're going to use z. Okay, so we have 4 conditions, and that I just talked about is the first one. So our population standard deviations are known. We have randomly selected samples. We have independent samples, okay? Again, that's what we did in the first couple of slides of this. When we have dependent samples, it's a different test, okay? So we'll get to that later. And then this fourth condition has been the same in Chapter 7 also. We have to have either normally distributed populations, that's what lets us use our z, or our sample size is at least 30, because then it starts to approach the normal distribution anyway. So we're running 2 sample z-tests here, okay? Now, if these requirements are met, then our sampling distribution, or our difference of all of our sample means, is a normal distribution. Now, the mean in the middle here is what we think our population difference is. Now, this is kind of what I was talking about before. When we assume there's no difference, then this middle is going to be 0, because mu1 minus mu2, if you assume there's no difference, that means the difference is 0. Okay? So, that means, again, if we took a bunch of means of differences and we subtracted them, our differences would look like this. Again, we're going to assume our difference is 0, and if it's not, that's when we're going to get some sort of z-score, and we're going to reject our null. So that wasn't really clear, sorry. So if again, we're going to assume it's 0, and then when we run our actual test, if we get z-scores that are extreme and far away from the mean, that tells us that it doesn't actually look like our mean is 0, okay? But again, we assume it's 0, and then we use our test to either reject that 0 or fail to reject that 0. Okay, now we have a new standard error formula. This is going to come up in our z-score formula. So when we use our z-score formula, it's going to look slightly different in this section, because we're dealing with differences instead of just actual values. Okay, so we're going to look at that z-score formula in a minute, but this standard error is going to be part of our z-score formula. Remember, our classic z-score formula is x minus mean over standard deviation, but we've seen this standard deviation change based on what we're doing. When we were doing a standard error, we had our x bar here, and then we had our sigma down there. Sorry, not sigma, our radical n down there. So our z-score has gone through kind of an evolution. This is just our next evolution in our z-scores. Okay? So, this is the same stuff that we've been looking at. It looks very familiar. Again, we're going to verify that all our conditions are met. So we have sigma from both of our populations. We have independent samples. We have either normally distributed situations or large sample size. So again, we're going to state our null and alternate. We're going to figure out our alpha. We're going to either, again, use your critical value, okay, or p-value, depending on what thing you're going to. You're going to determine whether you're going to reject or fail to reject. Here's our z-score formula. Okay, so I want you to take a second. I want you to write that down. But on the bottom here, I'm going to write this a little bit different. We're actually, of course, I'm going to make you do one by hand. Okay? Now, this formula looks like a lot, and it's, it's something, but it's not insane. I want you to think about this part right here. Again, mu1 minus mu2, so that's our population mean. Now, we don't know that value, but like we just talked about, we're going to assume that it's 0. So when we do this, this is just going to be 0. So really, this part of the equation, you don't have to do anything. It's just 0. Now, the bottom part of that equation is that thing from the last slide, our standard error. So it looks like this, your first sigma squared over your first n plus your second sigma squared over your second n. All of that under a square root. Okay? So take a second right now and write that formula down, because we are going to use it when we do our first problem. Okay, so here is our first problem. So our first problem says a credit card watchdog group claims that there is a difference in the mean credit card debts of households in California and Illinois. The results of a random survey of 250 households from each state are shown. The 2 samples are independent, so that's good. That's one of our conditions. Assume that sigma 1 is 1045 for California. Oops, that's supposed to say sigma 2 right here. That's sigma 2. Okay, and sigma 2 is 1350 for Illinois. Do the results support the group's claim? And use an alpha equals 0.05. Okay. I'm going to go forward for 1 second, but I'm going to come right back. Okay, I just wanted to see what was on there. Okay. So what we're going to do here, what I would always recommend you do in these situations, because especially now we have 2 groups of information. So we're used to kind of having a sigma, an n, etc. Now we have 2 groups of that. So I would definitely recommend, even if the problem doesn't give you something like this, I would write something like this as you do these problems. Just have a little chart with all the information. I'm going to add to the bottom here our sigmas. So for California, it said our X bar is 4777. Our N is 250 because they took 250 households from each. And then our sigma from California was 1045. And our sigma from Illinois was 1350. Okay, so again, this slide kind of gave you a little chart. I would make your own chart regardless here. Okay, so I want you to think about here what our mean, standard deviation, or sorry, what our not our mean or standard deviation, we already know those. What our null hypothesis, alternate hypothesis would be here, and that's where we're going to start. And then we're going to actually do the math and find us a z-score. Okay, so again, pause and do that for a minute. At least do your null and alternate right now. And then try to do the z-score again. Use that formula that we just wrote down. I have it on the next slide with all the work shown, so I don't want to go there yet and spoil. But try this and be careful, especially about how you put the bottom in your calculator. But if you have a nice, graphing calculator, like you should be able to put all of this in at once. Sorry, my handwriting, I'm trying to squeeze it up here. But it'll be nice and neat on the next slide. But you want to put all of this into the calculator at once if you can, because that's going to get you the most accurate non-rounded answer. Okay? So I want you to try that. Again, our answers are coming up on the next slide, and then they're coming up again. I have them in 2 different formats. The first one comes right straight from the book. So I'll be honest, I didn't do this one, but I did it on my paper. I have proof. But this is what the book had as the answers, okay? So we have our null and our alternate, okay? Are right here. Okay, then our z-score. Now here was the formula, and again, if you're trying to practice and get good with your calculator, do this please right now. Make sure that you can do this and have it come out to this answer of negative 0.82, okay? Now, this book version did the critical value. I'm going to show you that. I'm also going to show you the p-value as well, okay? So this was a 2-tailed test here. So let's talk about critical value first, all right, because that's how they did it. So this was a 2-tailed test at alpha equals 0.05. So what they did, and they show it here, is that when you have a 2-tailed test, you have to split that alpha in half. So over here, our left area is 0.025. And then you can do an inverse norm on your calculator to find out what this boundary line would be. Or you can look it up on your chart. Now, we also have, hopefully some of them at least memorized or written down, the most common critical values. 0.05 is one of our commonly used alphas, so that is on our list. And that corresponds with negative 1.96 and positive 1.96. So that means your rejection regions are anything beyond those. So lower than negative 1.96 or higher than positive 1.96. And our z-score, they marked it here, it's kind of light, so I'll show you. Our z-score was negative 0.82, which is right around there, which is definitely not in our rejection region. So that's what led to our decision of failing to reject. Okay? Now, if you're doing a p-value here, okay, so again, let's look at this. Our p-value is going to be found if you're using your z-chart. You look up negative 0.82 on your z-chart. when you look up negative 0.82 on your z-chart, you're going to find a left area of 0.2061. Again, see if you can find that right now. But this is a two-tailed test. That is the left area. So we have to do times 2. And that gets us to 0.4122. So that's our p-value. And that p-value is way bigger than alpha equals 0.05. So again, that also leads us to a decision of failing to reject. Okay? Now, or after, if we fail to reject, we say there's not enough evidence to support the group's claim, because their claim, they didn't mark it, the book is bad. Their claim was that there was a difference. Okay? It didn't say greater than or less than, it just said we think they're different. So that was the claim. We were unable to reject our null, so therefore we were unable to support the claim. And I do want us to think about this in chapter 8. I want us to take us a little step further and say, you know, if we weren't able to support the group's claim, then it doesn't seem like there's a difference in these credit card debts. So I want us to actually figure out what it means when we're doing that. Okay, now, so I know this is a little messier. Again, this came straight from the book. I will show you what I have on mine. Okay. Okay, so again, this is how we're used to writing it, kind of in more of a chart sense. So we have, sorry I couldn't get these to be little subscripts, but you should write them like subscripts. So mu1 equals mu2. Okay. Again, same z-score. Now, if I'm going to go into more detail on the calculator on example 2. I'm keeping it a secret on example 4. But if you, I know some of you guys are very logical, smart people, so you can probably figure out how to do it on the calculator. If you figure out on the calculator, you'll get this answer as opposed to this answer we got on the chart. Now you might be like, whoa, those answers look so different. They're supposed to be close. That is a difference of 24 10,000ths. Okay, so it seems, just because, you know, it seems like there's a bigger difference there than there is. It's not a huge difference, so that's fine. But again, I'm going to tell you the calculator on the next one, but if you were able to figure it out, you should have gotten that. Again, critical value was plus or minus 1.96, failed to reject, not enough evidence to support the claim. But then I like adding this now in chapter 8, so I want us to take it a step further, where after we make our decision and we interpret it in terms of the claim, I want us to actually figure out, like, what does that mean in the real world, okay? So it doesn't seem like these two states had significantly different credit card debts, okay? So now let's look at another example. Okay. So we're on example 4 now. Okay, so in example 4 says a travel agency claims that the average daily cost of meals and lodging for vacationing in Texas is less than the average daily cost in Virginia. Okay, so they say vacationing in Texas is less than the average daily cost in Virginia. Again, we're talking average, so we're dealing with a mean question. Okay. It says the table at the left, and the table is at the bottom. Here it is. So it says the table shows the results of a random survey of vacationers in each state. The two samples are independent. Okay, so assume that sigma 1 equals $19 for Texas, so I'm going to add that. That seems, oh no, that's sigma. I thought that was our average. Okay, so sigma 1 is 19 for Texas, and sigma 2 equals 24 for Virginia. Okay? And that both populations are normally distributed. That's good. We have alpha as 0.01. Is there enough evidence to support the claim? Okay, now, for this one, I'm using the calculator, okay, and I will tell you how to get there in a minute, but what I want you to do first is do your null and your alternate and all that stuff. Actually, that's it first. Okay, so first let's talk about our null hypothesis, and again, you should do it before I do it to make sure you know how. Okay, so our null, it says Vacation and lodging in Texas is less than the average daily cost in Virginia. So we know our claim is that Texas, which is mu1, is less than mu2, right? So Texas is mu1. You always want your mu1 here first on the left-hand side. Okay, so Texas is less than Virginia. That's what this says. Since that has no equality, that's going to go in our alternate hypothesis. So mu1 is less than mu2. That's our claim. Now, if our claim is that, or if our alternate is mu1 is less than mu2, then our null must be its complement. Mu1 is greater than or equal to mu2. Okay, now with that information and all of the information here on the chart, you now have a choice. You can use that same formula we used last time to find our z-score, or you can go to your calculator, which is what I'm going to tell you how to do right now. You have to be a little bit careful. It's, again, once you get used to it, it's pretty easy on the calculator, but you have to just be a little careful when you're going here. So what you're going to do is you're going to go to our favorite menu, Stat Tests, okay? Stat Tests, and we are now going to number 3, which says 2 sample z-test. Okay, so 2 sample z-test. Okay, now when you go there, be careful because the stuff is in, I don't know why they do it in this order. I think it's a strange order for them to put it in. But look and make sure you're putting the right information in the right place. So the first thing it asks you for is sigma 1, then sigma 2. Okay, so sigma 1, we have 19. Sigma 2, we have 24. All of this is also on the next slide, by the way, but I just kind of want to do it along with you guys. So we have sigma 1, we're going to put 19. We have sigma 2, we're going to put 24. So again, make sure you're paying attention to what it's asking you for. Then it says x bar 1, that's going to be our 234. Then it says n1. So again, the order, I think, first it says both the sigmas. I'm not really, we'd have to ask the TI people what the logic is behind this order. But then we have our n1, which is 25. I just put 19 there by accident. It's 25. Okay, then our x bar 2, which is from Virginia, which is 240. And then we have our n2, which is 20. Okay, so again, just pay attention as you're putting those in. And then you're going to pick the sign, as always, from your alternate hypothesis. So, I just left. Okay. So you're going to make sure you pick that less than sign, which is the second one. And then you should get all of your answers, which I will tell you in a moment. Okay? So try all that, see what you get. And I'll show you the calculator input and output on the next slide. Okay, so again, here's where we are. We are on a 2 sample z-test on our calculator. We put in our sigma 1, sigma 2, x bar 1, n1, x bar 2, n2. No, these are there twice. I don't know why. Okay, same thing. Okay, this was just the printing thing, not the calculator. We put our sign from our alternate, and then this is what your output should look like. So our z came out to negative 0.91. Our p-value came out to negative 1088 if you round there. Okay. If you did it on the chart, I also did it on the chart, then your p-value was, again, slightly different, but very similar. I'll show you that on the next slide. So again, check at this point, just make sure your calculator output matches this. And then while you're there, think about what should be your decision about your null hypothesis based on this, and then what your conclusion should be. So think about that now, because the answer is coming up in a second, okay? So here it comes. Okay, so again, we already talked about these. The critical value was negative 2.33. We had an alpha of 0.01 and we were running a left-tailed test. Okay, so again, we were in this, sorry, that drawing was bad. We were in this scenario where you were finding out this left-only boundary line. We had a fairly high p-value, so we failed to reject again. Again, not enough evidence to support the claim. Now this again is what we're adding in chapter 8, and I will ask you to do that on the test. So when we say there's not enough evidence to support the claim, it seems that Texas is not cheaper. We did not think this looked good. Now, we don't know if that means Texas is more expensive. We don't know if that means they're the same. All we can say is that we did not support this claim, so it doesn't seem that Texas is cheaper. This part here where we write it seems is super important. Okay, we have to be okay with uncertainty and the fact that we could be wrong. Maybe it is cheaper in Texas, but based on this math that we did, it does not seem that that is the case. Okay. All right, we got one more and then we're done. So, a survey indicates that the mean annual wages for forensic science technicians working for local and state governments are $55,950 and $51,100 respectively. The survey includes a random sample of size 100 from each government branch. Assume the population standard deviations are 6,200 for local and 5755 for state. The two samples are independent. At alpha equals 0.10, is there enough evidence to conclude there is a difference in the mean annual wages? Okay. Now this one, I definitely want to talk about the order that you guys are doing these in. This one doesn't say like mu1 is this or sigma 1 is this. If you're in a situation like that and you want to match my answer keys, what I have on the test, and not drive us both crazy, go in the order of the sentences in the problem. So this says working for local and state. So we're going to make local first and state second. And if you flip those, you can still get correct math, but I need to know which one you use. So you need to, if you're flipping them for fun, you need to explicitly tell me that you're doing that, because I'm going to assume that when I'm grading your stuff that you've put it in the order that the problem also put it in, okay? So we're going to call local as x bar 1. So we have local is 55,950 and state x bar 2 51,100. If anyone doesn't know, that's what the word respectively means. When it says like local first and then state second, that means the first one goes with local and the second one goes with state. Okay. Then we have for a sample size of 100 from each. And then we have assume that let me finish. Can't write and talk at the same time. So we have 100 from each, and then we have the standard deviations are 6,200 local and 55, 57, 55 from state. So again, even though this problem didn't give us a nice little chart like this, we made a nice little chart. So that way you're able to kind of organize your information. Okay. Now, I want you to do the whole problem right now before I say anything, or pause me, so you are able to see if you can do this problem from beginning to end, starting with your null hypothesis, ending with your real world application. Okay, so pause this right now. If we were in class, this would be like me walking around the room, seeing how you guys are doing. So do that now. Okay, and then we will give our answers here. All right, so pause it so you don't get spoiled. All right. So we have the question was, is there enough evidence to conclude that there is a difference? Okay, so that there is a difference was our claim, okay? Well, again, we don't know if it means one is less than or greater than. We just say there is a difference, okay? So then we have equality as our null. We have non-equality as our alternate. Now our test statistic, our z-score, came out to 5.73. That's a pretty giant z-score, okay? Think about if you're on your normal distribution. You're all the way like out here somewhere, very far. if you looked at your calculator, your p-value said 9.8 something something something, make sure you're reading all the way to the end of your calculator screen, because obviously you know that a p-value has to be less than 1 since it's a probability value. So 9.877 made no sense. But if you kept reading, there were a bunch of other numbers, and then it said e to the negative 9th power. Remember, that means we're moving our decimal point over 9 places. So that means there's 8 zeros in front of this 9. And again, if you're rounding that to 3 or 4 places, it's just a bunch of zeros. So it's basically 0 is your probability of us getting this type of sample if our populations are the same. So if our populations are the same, there's basically a 0 probability that the samples we got would exist. So that tells us that our samples are probably not the same, our populations are probably not the same, which is why we are rejecting our null, okay? So we're going to reject our null. That means we are able, finally, this is our first example where we're able to support our claim. Okay, so we're going to support the claim. And again, that claim was that there is a difference in the mean annual wages for local and state government. So that means it seems that there is a difference between the mean salaries in local and state wages or governments. Okay, but that's it. That's what this section is, okay? So it's very similar to the stuff from Chapter 7, except instead of comparing one population to a value, we're comparing one population to another population. So yeah, that is the end of 8.1, and make sure that you do your homework, and then we'll be good. So thank you for watching.